In this video, we look at an introductory example in section 3.6. So an intro example. This will be follow on with what we looked at in section 3.4, where we had a differential equation that was of the form A, B, C, D, and the eigenvalues of the matrix A came out to be complex numbers. Okay, so the example we're going to look at here is the differential equation in section 3.6, AY with initial condition y of 0 is y0, and the given information we have is the matrix A is 0, 1, negative 13, negative 4, and y0 is equal to 2, negative 2. Okay. First thing you're going to do is find the eigenvalues. Okay. You'll look at the determinant of A minus lambda I, which comes out to be minus lambda 1, negative 13, negative 4 minus lambda. Take the determinant of that matrix to get negative lambda, negative 4 minus lambda, minus 1 times negative 13. So you'll get lambda squared plus 4 lambda plus 13. Take that determinant, set it equal to 0. Recall that this is your characteristic equation. And use the quadratic formula to find that lambda comes out to be negative 2 plus or minus 3i. Okay. Things to notice about this example are the special form of it. Okay, the special form of this matrix. Notice that the first row is 0, 1. Okay, so if, for example, our solution vector y is y of t, v of t, then that first row of the matrix translates into 0, 1, negative 13, negative 4 times y v is equal to y dot v dot, which that first row translates into y dot is equal to v. That's what this first row translates into. Okay, so we're not looking at just any system, we are looking at a very special system where y dot is equal to v and v dot is equal to negative 13y minus 4v. There's a system of differential equations we solve, and we always know that our first step there is to find the eigenvalues. Okay. You can then proceed on to find the eigenvectors. Okay, we will leave these steps to you, giving you the answers that v1, which is the eigenvector associated with lambda 1, which is negative 2 plus 3i. The eigenvector is going to be negative 2 minus 3i and then 13. And the associated eigenvector for v2 and lambda 2 are the conjugates of v1 and lambda 1. Okay? So you know then that you can find two solutions, y1 of t and y2 of t are solutions to the differential equation of the form e to the lambda 1 times t times the first eigenvector, and similarly for y2. So that would be your third step. I'll leave you to find those. And then you need to proceed on to forming the superposition principle to find y of t, and you have two choices here. You can find k1 times y1 of t plus k2 y2 of t, and you can use the initial conditions y of 0 is equal to k1 v1 plus k2 v2 to solve for k1 y1, k1 k2. If you proceed down that route, you will get that k1 is equal to negative 1 over 13 minus 11 over 39i, and K2 is equal to negative 1 over 13 plus 11 over 39i. Okay? And then you would have to go down the route of finding, using Euler's formula. Euler's formula on y of t to get rid of the complex values, which will lead you to y of t is equal to the first entry will be e to the 2t, 2/3 sine of 3t plus 2 cosine of 3t. And the second entry, as promised, which is your v entry, is just going to be y dot of t, where this first entry is y of t. So if you can find the first entry, then you'll know the second. Okay? So that's what happens if you progress down the road of using y1 and y2. Okay? If you should prefer to do y of t is equal to c1 y1, the real part, plus c2 y1, the complex part, which actually is probably an easier route in this problem. And then go down this route where and then simplify and use your initial conditions, that c1 will come out to be negative 2 over 13 and c2 will be negative 22 over 39. Okay. The reason we're doing this example is because it's an example in the textbook, so we thought we would show the details from it, and therefore y of t is c1 y1 real plus c2 y1 complex, and that will simplify to the same answer. Okay, so there's the linear algebra route to solving this particular differential equation, okay, with the given initial conditions. Okay, let's take a look at this example and what it meant in the context more specifically of 3.6, which is related to what's called the mass spring damper. We're looking at trying to get details of everything that's going on with the mass spring damper, and evidently this matrix is something very related to the mass spring damper. So we'll go ahead and take a look there. I would like to call your attention to the fact right here, without going through all these details, we could have gotten a lot of information from just knowing the eigenvalues. If you compare to what happened after we went through all the details, right, you can see the structure here, that y of t, right, the first entry, this isn't e to the negative 2t when we factored it out, sorry, that the eigenvalues completely determine your solution. So if you're looking for the general solution to y for this differential equation, notice that the real part of the eigenvalue led to the e to the minus 2t. And then we got some constant times cosine of 3t plus c2 times sine of 3t. The 3, being the imaginary part of the complex number, is showing up in the frequency term. Okay, this is typically what I'll call omega. Omega is 3 in this problem. And here the negative 2 is the real part of the eigenvalue. It's showing up in this exponential term. And then you would just have to use the initial conditions to find the constants, C1 and C2, okay, and then you would, once you knew y, after you knew the constants, then you could find the velocity v by taking the derivative of what you've known here. And that would lead you to the same answer. So a couple different routes, but the general observation we're seeing is that we can jump from the eigenvalues and jump right into this general solution if we want, okay? And then find the constants, maybe not necessarily using the linearity principle, but doing another method, which I'll show on the next page, okay? So let's dig in a little bit more to this example. You can see that the solution that we got, right down here in the bottom right corner, if we look at the solution or the example that was in the book, okay, we can see that the book was solving this differential equation, and they sketched us the solutions, right, and the time plots, and they also gave us the phase plane. Okay, notice that y of t is this solution right here. Notice that at time 0, y of 0, we're saying those initial conditions are 2, just for the nearest integer to there. So it looks like the initial conditions are about 2, which is what we chose. And the fact that the waves are oscillating but getting smaller and smaller in amplitude was due to the fact that there was the e to the minus 2t in the solution. And then we knew that we had something cosine of 3t plus something times sine of 3t. And the 3 there, the frequency, or the angular frequency, was 3, and that's related to t, the period. The period is 2 pi divided by omega, okay? And omega is 3 in this case. So the period, the time it takes to go from peak to peak, or from peak to peak, these peaks here, is about 2 pi over 3 seconds it took to do that. Okay? All right. So let's dig into a topic that's specifically covered in the section 3.6, and this is what the textbook calls a free gift from the math department. Okay, and we know that we can turn this system of differential equations, this second order differential equation, you can convert this into a system. Okay, as we've done several times now. This differential equation is a mass spring system. It's of the form m y double dot plus by dot plus ky equal to 0. Okay, divide through by m. Okay, and then let y dot is equal to v, and therefore v dot will be negative k over m y minus b over m v. And you can see there that the matrix for this differential equation, the matrix of this second order differential equation, written as a system, is 0, 1, negative k over m, negative b over m. Okay, so here we're looking at, this is a mass spring damper differential equation, second order, and its mass spring dampers turn into the very special matrix where 0, 1 is on the first row, and the stiffness, the damping coefficient, and the mass show up in the matrix A. Okay, so the free gift from the math department is to get to the eigenvalues a little bit more quickly. Okay, so the trick here is to take a guess at a solution. Guess a solution to this second order differential equation. And we're just going to focus on the differential equation itself. So your guess a solution is going to be e to the st for some values of s. This is a good guess because the exponential, when you take derivatives of it, it is itself. So you have a chance when you're taking these derivatives and second derivatives that you'll get the same thing back again and get a chance for every term in the differential equation to cancel out and give 0. Okay? So if you proceed down this route and guess your solution, that you've guessed that y is e to the st, then y dot is s e to the st, and y double dot, the second derivative, is s squared e to the st. If you take those and plug them back into your differential equation, then you will get an equation that's s squared plus 4s plus 13 e to the st is equal to 0. And this should look very familiar as the characteristic equation. So this equation is equal to 0 only if the s squared plus 4s plus 13 is equal to 0, which was your characteristic equation, and therefore we know that s is equal to -2 plus or minus 3i. Okay, so that tells us that the values of s that will work in this exponential are the eigenvalues of this matrix A. And this guessing method gets you to the characteristic equation in the same way that taking the determinant of A minus lambda I will get you the characteristic equation. So where does this leave us? This leaves us with, we found the eigenvalues of the differential equation, so to speak, in a couple different ways. Right? So that means that if we're looking at the differential equation y double dot plus 4y dot plus 13y equals 0, and you have initial conditions to -2, which means that we have our initial position of this mass on a spring as 2, and you have the initial velocity as -2, then we know that the solutions to this differential equation are going to come out to be e to the -2 plus or minus 3i times t, okay, which we know is going to turn into e to the -2t cosine, I'm sorry, I skipped a step there, e to the, just putting quotes around this, e to the plus or minus 3i times t. Okay, and you'll get to use Euler's formula to lead you to e to the -2t, cosine of 3t plus I sine of 3t. Right? Now, we know what's going to happen here if you combine these in the right way. This leads you to your general solution. We got the complex eigenvalues. We know that our solution for y is going to be e to the -2t, some constant cosine of 3t, plus some other constant sine of 3t. Okay. We just don't know what those constants are, right? But you do know that the initial position is 2, okay? And we know that the velocity for the mass spring system is the derivative of y, okay? If you take the derivative of y, okay, that'll lead you to c1, okay, so you have to take the derivative here. Okay, c1 times the derivative of e to the -2t cosine of 3t plus c2 times the derivative of e to the -2t sine of 3t. Okay. Take this derivative with the product rule. Okay. Take the derivative here with the product rule, which will lead you to c1 first times the derivative of the second. Derivative cosine is -3 sine of 3t plus -2 e to the -2t cosine of 3t, that's the derivative of the second, and then c2 e to the -2t, the derivative of sine is cosine of 3t times 3. It's kind of a big mess here, but you're just trying to stay organized. So the derivative of e to the -2t is -2 e to the -2t sine of 3t. So the first trick is to take the derivatives correctly, okay, which we've tried to do here. Okay. Notice that e to the -2t is in common again, so you can factor out the e to the -2t. Okay. And you'll get negative 3c1 sine of 3t. You will get, let's see, minus 2 c1 cosine of 3t. And then you'll get terms when you factor out down here e to the negative 2t, 3c2 cosine of 3t. Okay. And then you'll get minus 2c2 sine of 3t. Thanks. And there's the formula for your velocity. Okay. Now, what does this buy you? This buys you that you know the general solution for y of t, but you just don't know c1 and c2. So you have to find a system of equations to solve. Okay? But you know that y of 0 is 2, but you also know that if you put in 0 for t, e to the 0 is 1, you'll get c1. Okay? This will cancel, and this is where you get the 1 from, so you'll get c1. If you put in your initial velocity, you know that that was negative 2 from the initial conditions. Put 0 everywhere for t, which will lead you to negative 2c1. This is the only term that survives in the first line. And the cosine is the only term that survives in the second line, so you'll get plus 3c2. Okay? So now you have a system of equations to solve where you can find c1 to be whatever number that comes out to be, and c2 to be the other number. All right? So you have two choices when you're solving these differential equations. You can use the exponentials to get to the characteristic equation quicker. That will lead you to your eigenvalues. That leads you to your general solution. Has to be of the form e to the real part of the eigenvalue times t plus c1 times cosine of whatever the imaginary part of the eigenvalue is. And then you have to solve for c1 and c2 using your initial conditions. Okay. The constants that you know you're going to get were from the previous solution when we went through and solved this as a system. So you know what your c1 and c2 are going to come out to be. Okay, it'll come out to be these answers. Okay? So that's an introduction to the section 3.6. Using a couple different techniques, and you can use whichever technique you find the most easy to use. My preference is always to go back. It just seems to organize things for me, but my preference is always to use the linear algebra techniques. But you have other techniques in this section if you choose to use them.